So we have been talking about quantum field theories and discussing the current understanding of what are the fundamental things that make up the universe, the fundamental particles that make up the universe, and the fundamental forces that govern their interactions. And I claim that the reason for doing this was that we needed to understand these things in order to understand what the universe was like when it was very, very young. So that's what I want to talk about today. I want to connect these two ideas. Let's go back to when we were talking about the Big Bang. We said that one of the big pieces of evidence for the Big Bang model of the history of the universe is the fact that we see this cosmic microwave background radiation coming at us from all directions in space. And we said that this radiation came from an era that we call recombination. It was the time in the history of the universe when there were the first atoms. An atom is a nucleus and an electron that are bound together. During the recombination era, the universe was mostly hydrogen with some helium, maybe some deuterium, some heavy hydrogen, but the universe, just like it is today, 90-some% hydrogen, was 90-some% hydrogen, and the electrons in those hydrogens were bound to the protons as an atom, a neutral atom. This era ended the previous era ended about 300,000 years after the Big Bang. So the universe was a very, very tiny fraction of its current age. The size of the universe would have been only a few 100,000 light years, which is about the size of our Milky Way galaxy. So if we imagine taking every galaxy in the universe, the hundreds of billions of galaxies that are tens of billions of light years away from us, and squishing all of those galaxies into the Milky Way galaxy, that is how much energy we're talking about in this era. The entire universe, everywhere in the universe, would have had a temperature of thousands of degrees, about the temperature of the surface of the sun. Even though the universe was very hot, everything was made of atoms, and because everything was made of atoms and the electrons were trapped in their atoms, light could actually travel from one place to another. Remember, an electron in an atom can only absorb certain frequencies of light, certain energies of light, and other energies of light can just go right on by. So the light that we're seeing from the recombination era, the cosmic microwave background light that we're seeing, is this light that was bouncing around this little universe when it was thousands of degrees everywhere, and some of that light is just now getting to us at our location in space. That light has been redshifted by the expansion of the universe from the very high energy light that would have existed at that time to long wavelength microwave radiation, which is what we see when we see the cosmic microwave background. Before the recombination era, it was hotter. The temperature was not a few thousands of degrees, but a few million degrees or even billions of degrees Celsius or Kelvin. That means that you could not have an atom the way we think of an atom as a neutral system with a proton and an electron that are bound together. If two atoms hit one another at temperatures of millions of degrees, they come apart. So the material of the universe at this time, when the universe was just a few thousand years old, all the way back to when it was just a few minutes old, the matter was ions, protons that have been stripped of their electrons. So the protons are bouncing around free and the electrons are bouncing around free. So not hydrogen atoms, but hydrogen ions and free electrons just bouncing around the universe because it's too hot to have an electron bound to a proton. Another particle would hit it and break it apart. So this ionized hydrogen made up most of the universe, free protons and free electrons. And because the electrons are free and the protons are free, they can absorb light of any wavelength or any frequency, any energy. So light could not actually travel from one place to another during this era. It would have been emitted by one particle and immediately reabsorbed by another particle. So the universe was essentially opaque during this time period. Light could not travel from one place to another, which means that there's no way for us today to see anything that was happening during this time period because light wasn't traveling from one place to another in the universe. It was just bouncing from one particle to the next particle, just like in the interior of the sun. It takes hundreds of years, for maybe thousands of years, for an individual photon to make its way from the core to the surface. So we're talking about a universe where the age was anywhere from a few minutes to a few thousand years. The temperature was anywhere from a few million to a few billion degrees. And the size of the universe was smaller than the size of Mercury's orbit around the sun. So imagine taking every star in every galaxy in the whole universe and squeezing it into our inner solar system. That's how small the universe would have been at the beginning of this time period that we call the Nucleosynthesis Era. Why do we call it the Nucleosynthesis Era? Because if the temperature is millions of degrees everywhere, and that is the temperature of the core of our sun or the core of a star, that means that everywhere in the universe, it was hot enough for hydrogen to fuse into helium. So the whole universe was essentially like an enormous stellar core. The synthesis of protons into neutrons and deuterium and helium and light elements was happening everywhere in the universe for a few thousand years. Now we can't see any light from this time period, because the universe was opaque. Light couldn't get around. There's too much stuff to absorb it. The density was too high. So how do we know that this nucleosynthesis era happened? How do we know that there was this time period in the universe where hydrogen was fusing into helium everywhere? Because we know how fusion works. We know how much energy it takes to fuse hydrogens together. We can calculate if the temperature was so-and-so and the size of the universe and the density was so-and-so and this age lasted for a certain amount of time, we can calculate how much hydrogen should have fused into helium during that time period. We can do an estimate, a theoretical calculation, of how much of the universe's hydrogen should have been converted into helium. Then we can look out into the universe and see how much helium there is today, and see whether or not that prediction is correct. And we wouldn't be talking about that if it wasn't. In other words, when we look at the universe and look at the abundance of helium relative to hydrogen, we can say that it's about what our theories of nuclear fusion would predict would happen during this nucleosynthesis era, if the whole universe was like a big stellar core for thousands of years. And the answer is, I don't remember exactly, 96% hydrogen and 4% helium or something like that. But the prediction basically checks out. So our evidence that this happened is indirect evidence that comes from the abundance of light elements like helium and some other light elements like lithium and beryllium and so on. So we are pretty confident that we understood what was going on in the universe when it was just a few minutes old, just a few minutes after the expansion began, and when its size was smaller than our inner solar system, which is fairly remarkable that we can say something about what the universe was like in those extreme conditions. What if we go back even further, when the universe was even smaller and even denser? When the temperature of the universe was tens of billions of degrees, you could not have a helium nucleus. A helium nucleus with protons and neutrons stuck together would be banged into by an electron or a proton and just broken apart. So it was so hot that you couldn't have anything but protons, neutrons, and electrons. So the whole universe was nothing but free subatomic particles. Protons, electrons, neutrinos were bouncing around the universe. Light, obviously, photons of light were bouncing around the universe. Heavier particles like the muon and the tau, and all of those particles that we discovered in the 40s, 50s, 60s, 1970s, 1980s, all of these heavier sort of versions of protons and neutrons could exist during this time period. And every photon of light had enough energy to produce a pair of particles, a proton and antiproton, or a pion and antipion, or a lambda and anti-lambda. So during this era, there were particles popping in and out of existence. The photons of light were energetic enough to create matter from E equals mc squared. You can create matter if you have a certain amount of energy. Now, the most stable constituents of matter turn out to be the proton and the neutron and the electron. But during this time period, we're creating all sorts of particles all the time. The age of the universe would have been something like a 10,000th of a second, a few tens of microseconds old. The temperature of the universe would have been tens of billions of degrees, and the size of the universe, we're talking about taking all the matter and the energy in the universe today and compressing it to the size of about a kilometer. So the size of a few city blocks or a neighborhood, or maybe a little bit bigger than the Richard Bland College campus. Maybe a little bit smaller than, I don't know how big the campus is, probably smaller than campus if you count the fields and the regions and the outskirts of campus. How do we know what the universe was like when everything had this much energy? Because that's what we are doing on our particle accelerators when we bang two protons together and make a J psi or a lambda or one of these weird particles that we don't encounter in everyday universe. We know the laws of physics that govern all of this behavior. It's the laws of QED and QCD, the quantum field theories that we have talked about. So while we might not have any direct evidence that is left over, any relics from this time period in the history of the universe, we do think that we know how matter and energy behave at these energies, because we can create those energies on a small scale in our particle accelerators. We think we know the laws of physics that would be working at temperatures of tens of billions of degrees everywhere, because we can make little baby universes. They're not really baby universes. We can make a little test in a particle accelerator of how particles behave when they have that much energy. And we think we know what they do because the predictions of QED and QCD are quantum field theories that describe these interactions. They all work at those energies. So we think we know what was going on in the universe a few thousandths of a second after the Big Bang, based on our theories of particle physics. They are able to describe how matter and energy behave in those conditions. What if we go back even further than that? If we go back even further than that, what we realize is that at a certain temperature, say 1 trillion degrees, or 1,000,000 trillion degrees, or 1,000,000,000 trillion degrees, or 1,000,000,000,000 trillion degrees, you can't even have protons and neutrons. Because if two protons hit one another with enough energy, it overwhelms the force that holds together the particles inside of there. All of those particles that we talked about in the last slide, proton, neutron, pions, kaons, lambdas, upsilons, J psis, whatever, they're made of quarks inside. All of these nucleons are made of quarks inside. And we said when we talked about QCD, the theory of the strong force that holds quarks together inside a proton, that normally that force is so strong that you can't get the ups and downs apart from one another. And the reason is because the gluons themselves feel that strong force. But if everything in the universe has enough energy to overpower that force, there would have been a time when two protons colliding with one another, or two neutrons, or a proton and a neutron, or a pion and a kaon, any two particles made of quarks, when they crash into each other, would release the quarks from their confinement. So, just like there was a time period when the universe was so hot that hydrogen atoms could not exist without being broken up, making a hydrogen plasma, there was a time period before that where particles made of quarks colliding with one another broke the quarks free into this thing called a quark-gluon plasma. A quark-gluon plasma is just a mess of quarks that have been freed from their confinement because they've been knocked out by these huge energies, and the gluons are interacting with all of the quarks, and they're interacting with each other in this kind of mess of free quarks and free gluons. So something like a few trillionths of a second after the Big Bang, when the temperature was trillions of degrees or even trillions of degrees, the whole universe would have been a quark-gluon plasma. The only particles in the universe would be quarks. And I should have added the other colors, flavors of quarks in here as well. I should have added the charm and the strange in the top and the bottom to this picture. And leptons like the electron, the muon, the tau, neutrinos, just free particles zipping around, but the quarks broken free of protons and neutrons. How do we know? By the way, how big would this universe have been? We're talking about the universe being this big, okay? About the size of a softball, 10 centimeters or so. So we take all the stars and all the galaxies and the whole universe and squish it down to the size of a softball. What would that softball be like? It would be like this. It would be a quark-gluon plasma of free quarks, free gluons, free leptons, free neutrinos, just bouncing around in there with a huge amount of energy. Do we know that this really happened? Well, we don't have any direct evidence of this time period from the history of the universe, but we do know that we can create the state of matter in the laboratory. We have created, by colliding heavy atomic nuclei with one another, by colliding two lead nuclei or two gold nuclei with one another, for a split second, created effectively temperatures for just a few dozen atoms of trillions of degrees. And what this is a picture of is a detector from a particle accelerator. So the beam is coming this way and this way. So there are two beams of atoms that are going towards one another, or nuclei that are going towards one another, and they collide right here. And every one of these lines coming out is some subatomic particle. It's an electron, it's a muon, it's a tau, it's a pion, it's a whatever. What can we tell from this graph? Well, you and I can't tell anything from this graph, but if we analyze the energies and trajectories and charges of all these particles and trace them back, what we discover is that the state of matter that led to all these particles flying out was probably a quark-gluon plasma. That this end product that results from this, what are all these particles? They're all the quarks, when they cool off, zipping back together into trios and doublets and then flying out of the detector. So for a while, there was a quark-gluon plasma where all the quarks were free, and then they paired up and trioed up into pions and kaons and protons and neutrons and came flying out of the detector, and this is the detection that results from that. So we know we can make a quark-gluon plasma. We know how much energy it takes. We know its properties, sort of. So we think we know what the early universe would have been like, what would have been happening in the early universe a trillionth of a second after the Big Bang. There were no stars, there were no galaxies, there were no structures. There was just free particles, quarks, gluons, electrons, neutrinos, and so on, just interacting with one another. Can we go back further? What happens if we try to go back before the quark-gluon era? What happens if we try to say what would be going on in the universe when the temperature was more than 1 trillion degrees? One thing that happens during this era that we haven't talked about in class yet is a sort of temporary exception to the Big Bang rule that the universe kind of expands fairly linearly, fairly uniformly. There are reasons to believe that during this time period, this first trillionth of a second, there was a time period when the universe expanded exponentially fast, from the size of a proton to the size of a softball in the time span of 1 trillionth of a second. That idea is called inflation. That time period during which this happened is called the inflation era. It's similar to the idea of dark energy, where right now the expansion of the universe is accelerating. There was a brief period in the early history of the universe where it accelerated exponentially fast, just for a little time, and then settled into its fairly uniform expansion. I don't want to go into the reasons why we think this inflationary era happened. It has to do with the fact that when we look at the density fluctuations in the universe, how the density is different from one place to another. We looked at this when we looked at the pictures of the cosmic microwave background radiation, how it wasn't uniform. There were places in the early history of the universe that were a little hotter than others, places that were a little colder than others. That those fluctuations are very small. And one reason that they might be very small is if there was a time period where the universe expanded really, really quickly, to kind of even out those differences between density in one place to another. Like I said, I don't want to get into it right now because it seems like a digression. Maybe your book has a section on inflation, and I'll point you towards that just to read it and try to understand why we believe this happened. But this is when we think it happened, during that kind of time period, about 1 trillionth of a second after the Big Bang. What if we go back further? If we go back further, beyond a certain temperature, and that temperature would be something like 10 to the 30th degrees. What's that? 1,000,000 trillion degrees. When the whole universe was smaller than the size of a proton. We reach that place where our theories of quantum mechanics and our theories of general relativity don't really play nice together. Essentially, any particle with this much energy would have so much energy in such a small space that it would become a black hole. So does that mean the whole universe was nothing but black holes? Well, probably not. What that probably means is that our physics is not up to the task of talking about what was going on in the universe during this very, very short time after the Big Bang. That's 10 to the negative 40 something seconds. A trillionth of a trillionth of a trillionth of a second. Smaller than that. A millionth of a trillionth of a trillionth of a trillionth of a second. So the fact that we don't have a unified theory that describes how to combine particle physics with the physics of space-time, and the reason we need to combine particle physics with the physics of space-time here is because all of space-time was the size of a subatomic particle. The whole universe was smaller than a proton. So obviously we need to have a theory that can describe that much matter and energy in that small a space. And when we do that, we know already by now that we get singularities. We get answers that don't make any sense. So the Planck era is just a signpost that points out where our physics stops working. During this time, it may even be that the difference between space and time and matter and energy would have been meaningless, that they would have all been the same thing. And you might say, how can space and time and matter and energy be the same thing? The answer is we don't know, because we don't have a unified theory. This is what we're trying to figure out. So the Planck era is a dead end for our understanding of what was going on in the universe. We think we understand what atoms that are 1,000 degrees do, what plasma that's millions of degrees do, what nuclei that are billions of degrees do, what quarks and gluons that are trillions of degrees do. We have no idea what matter and energy do when their energy is equivalent to a million trillion degrees. We simply have no answers. When we have a unified theory, when we have a unified theory, maybe we will. Maybe we can talk coherently about what was happening during this time period. But any attempt to go earlier than this time period, to go earlier than this time when the quantum nature of space and time becomes important, is doomed to fail. Any attempt to talk about the Big Bang event, that moment that the universe started expanding, is going to run into the fact that we cannot talk about what matter and energy do when our equations of physics give us a singularity. If we go back further and further and further in time to time equals 0, we reach a situation where the size of the universe is 0, its temperature is essentially infinite, because we've got a finite amount of energy packed into an infinitesimally small space, and we can't say anything at all about it. So we don't know what the Big Bang event was like, because we can't get past that point where our quantum theories and our relativity theories, our theory of general relativity, we can't get that past that point where they stop playing nicely with one another. Does that mean that when we have a unified theory, we'll be able to understand the Big Bang event? Maybe. Maybe not. Maybe it'll raise a whole new set of questions. It's tempting to ask about the Big Bang. Well, what caused it? What made it happen? What made the universe start expanding? Right? That's a natural question to ask, because we can ask that question about everything else that happens around us. What caused that? Okay, well, what caused that? Okay, well, what caused that? Well, the idea of a cause presumes a before, right? Something happened before that thing to cause that thing, which means talking about what caused the Big Bang would require talking about what happened before the Big Bang. And it just may be a fact that talking about before the Big Bang doesn't even make any sense. Time is something that we measure from the Big Bang. The Big Bang was the origin of matter and energy and space and time. I almost said before the Big Bang there was no time, but that doesn't make any sense. There was no before the Big Bang. Asking what happened before the Big Bang is almost like asking what's north of the North Pole. Anywhere I go on the Earth, I can go north until I get to the North Pole. Once I'm at the North Pole, I can't go north anymore. Every direction I walk is south. Which direction is north? Is it that way? That's up. That's off the earth. If you go up, you're not on the earth anymore. If we think of space and time as being this closed, curved, four-dimensional bubble, then asking what happened before the Big Bang is like asking what is north of the North Pole. There is no before the Big Bang, just like there is no north of the North Pole. Time is a coordinate system that's measured from the Big Bang, just like latitude is a coordinate system that's measured from the North Pole. If anything, before the Big Bang means outside of our universe. If there was a cause to our universe, if there was a before our universe, it is not really part of our universe. It is outside of our universe. Can we talk about things that are outside of our universe? Is that kind of talk scientific? I would argue no. That asking questions about things that are outside of our universe is by definition not scientific, because you can never observe anything outside of the universe. And if you can't observe it, you can't scientifically test whether that statement is true or not. So the question of what happened before the Big Bang or what caused the Big Bang may just be an unscientific question, meaning that it's not a question that scientific methods can answer. It is literally a metaphysical question. It is beyond physics. One question that is tempting to ask is, why does the universe exist? Why is there a universe instead of no universe? Well, is that really a scientific question? Are why questions like that scientific questions? Or are they philosophical questions? Or are they nonsense questions? Different people will disagree about those three options. What can we say? We can say that we have no hope of answering what happened before the Big Bang until we can answer what happened at the Big Bang. And we have no hope of answering that until we have a unified theory that can get us beyond that Planck time, to that earliest question of what matter and energy would have been like at these very, very extreme conditions, very huge energies in very small spaces. So we're stuck for now, I think, until we come up with a unified theory. Now, what do we do in the meantime? In the meantime, look, we know things about physics, we know things about astronomy, we know how the universe works. Can we make guesses about what happened before the Big Bang? Sure we can, but those guesses are speculation. So you will hear scientists talking about universes that expand and contract in an infinite cycle. You will hear scientists talking about a multiverse, where there are many universes all existing at the same time in a super universe that has more dimensions than our universe, and universes can branch off of one another, and it's kind of foaming, bubbling, infinite multiverse of universes coming in and out of existence. Is there any reason to believe that? Absolutely none at all. Is there any reason to listen to scientists when they start talking like that? Not much, other than it's fun. And if you like believing in, multiverses from science fiction and hyperspace and higher dimensions and all that stuff, sure, that's fine. But that's not science. That's speculation and borderline fantasy. So we have to be careful. We have to know what questions are scientific ones and which ones we can answer. And we have to know what the limits are of our current scientific theories. Right now, the limit is a trillionth of a trillionth of a trillionth of a second after the Big Bang, which is pretty good. If I tell you, yeah, we basically understand most of the things that happen in the universe back to a trillionth of a trillionth of a trillionth of a second after the Big Bang, your reaction shouldn't be, well, forget about it. Scientists don't know anything. Right? We know a lot about what the early universe was like. But we will always be hampered by this roadblock that is currently standing in our way. I'm not going to get into the multiverse and higher dimensions and some of the speculations about what might have been going on before, quote unquote, the Big Bang. You can find stuff about that if you poke around on YouTube, but I would caution you First of all, to make sure that what you're listening to is not just crackpot nonsense by people who are just making stuff up. But even when real scientists talk about this stuff, there are certain scientists, Brian Greene, Michio Kaku, even Stephen Hawking when he was alive, wasn't always careful about telling his audience of non-scientists, all right, here is where the science stops and here is where I'm speculating. Right? Here's where I've gone beyond the boundary of what we can currently prove. Prove is a bad word in science, right? What we can currently support with observation and experiment. There are no observations or experiments that tell us anything about what was happening in the universe a trillionth of a second after the Big Bang, and there may never be. So, where does that leave us? That leaves us with a concrete goal, which is a unified theory. And once we have that, if and when we have that unified theory, we might be able to address some of these questions about that first trillionth of a second, and then we'll have a clear idea of, is it possible to say anything about what the universe was like possibly before that? And if it's not, maybe it's not. Maybe science doesn't have the tools to answer every conceivable question we can ask about the universe. And we have to decide, as people who accept science as a generally good method for figuring out what's going on in the world, are we happy, content, satisfied with that answer? That maybe science never will give us the tools for that, and we'll have to lean on other kinds of inquiry to answer those questions? That's a question you have to answer for yourself.